That's gone half past, so I guess we ought to be getting going into this. Just give a quick introduction to who I am while I let stragglers walk through the door. But I'm Alisdair Meredith. I currently work at Bloomberg in New York. And for my previous sins, I used to be the library working group chair for the ISO C++ committee, around about the C++14 era. And this talk is titled, or retitled, I've jumbled the words around since the original submission, to make a little more sense now, you'll see by the end, ignore, inform, enforce, assume. And this is a talk, oddly enough, about contracts. And so we'll talk in two parts. The first part, we're going to talk about what contracts are and why they're important to writing software, and that we have a good understanding and intuition for what a contract is. And that's by about the first 2/3 of the material. And then we're going to switch and talk about an open source library, BDE, that I happen to work on at Bloomberg, that has a particularly nice facility for supporting checking and enforcing your contracts. So we're going to go through a workflow using this library as an example. I recommend you check out the library and use our tool, that's why we provide it, but the actual workflow we're going to work through could work with any reasonable library that's trying to address this kind of a problem. So we'll start with the basic definition. What is a contract? Well, we can go down to the Oxford English Dictionary and get it's a written or spoken agreement between a variety of agencies. It's not quite what we're talking about in software. It's a good starting point, though. The interesting words here are an agreement and enforceable. So my definition when I want to think about this in terms of what is a contract when we're writing software, it's an exchange of promises between a client who's going to call some kind of software API and the provider of that API. It's probably, 9 times out of 100, it's a provider who's going to provide that contract. We're going to document the promises we're going to give you and say, as long as you satisfy the promises you told me you were going to satisfy, I promise you're going to get the behavior you expected. That's a contract in a nutshell. When we're trying to, the key issue is the provider has the information to enforce the contract, and it's a client that can then detect and report bugs. And one of the interesting, important aspects is there's two parties in a contract. You cannot unilaterally change a contract on either side. So we have to have a clear agreement if this is going to work at all. So examples of contracts in practice. Well, the one I work with is a C++ standard. I'm saying 1,500 pages because that's C++ 17. Who knows what 20 will be? But, the C++ standard, in terms of what it gives you a promise that if you give it source code that conforms to the rules of the language and the abstract machine, when you run that program, it will give you behavior that corresponds to an interpretation of those rules. If you violate those rules at any point, within the resource limits of the environment, if you violate those results at any point, well, for a set of rules, we're going to say, for an invalid program, we're going to report an error to you. You'll get to know where you violated the contract. That's part of our terms of the contract. We spell this out. And if you give me a program, I gave myself a, as we sent with my slide, sorry. Yes. We promise that we will report at least one error. Moving on, so if I lose myself, I have to keep moving because there's quite a lot of slides here. So if I violate the contract, it might or might not be, my program now might or might not behave as you expect. And the consequence of that is what we call undefined behavior, which is a bit of a bogey term in C++. But it's actually a really useful thing when you're trying to specify a contract. It says when you don't honor the rules of my contract, all bets are off. The C++ standard specifically calls out time travel can happen. And it exploits this when it does backpropagation with its optimizer. It actually uses and says, if you said you're not going to do this thing, I'm going to rely on that. And the impact is the bug that you are going to have as a consequence of violating that contract might happen even before you execute the code that has that bug. That is the nature of the time travel clause. Because the optimizer says you couldn't get there So I change this program that otherwise looked valid over here because my contract says we can do that. Another example of a contract in another language, Java, takes a similar approach. That we have a contract that you give me a well-formed program, I'm going to translate it according to the same rules, and then it can run on the Java virtual machine of the same version. And again, same guarantee of execution. The difference with Java is there are no undefined behaviors in the Java contract. Java promises in every situation it's going to detect errors, even at runtime. And it might turn those errors into an exception or some other kind of error behavior, but it tells you there will be an error detected and reported either at runtime or compile time. It's not quite fully specified behavior because you might have an option of 2 or 3 things the Java runtime machine might be doing, but it's gone the other way and said, we think it's so important that there's no undefined behavior in our contracts. We've gone the extra mile and given you a whole language built around having no undefined behavior. And that's one of the different approaches and one of the key virtues or sins of the Java and C++ communities, depending upon how you're approaching your language. I'm just trying to give a bit of insight as to how contracts have a philosophy behind them and how you're going to build a coherent system. You need to set your priorities. So, basic notion of a contract is hopefully some familiar terms. We have preconditions and postconditions. Preconditions are the promise that you expect of the people calling your API. Postconditions are your promises for this is a behavior I'm going to execute. Other familiar terms you might have there are invariants, to say these things are always true throughout the running of the program. And the error reporting is error reporting if you violate your preconditions, part of your contract or not. So just got some more quick show of hands. Who thinks that I need to document my error conditions for what happens when you violate my contracts? Who thinks I don't? Who's just waiting to see where this is all going? Okay, still not got half of them who raise a hand at all, so I'm lost. Sorry. Yes. Error reporting is a part of your contract if you want to support users handling and dealing with those errors. So it's definitely within the scope of what you will document for your contract. Doesn't mean you need to handle every error, but it does mean you need to document those that you claim you can handle and your users can then respond to. So, preconditions. Preconditions are the promise that you expect the client to honor when you're writing your API. So you better document what you expect them to do. Otherwise, they're perfectly free, feel free to call you in any way that satisfies the constraints you've given them. The implication is the client then has no expectation if they call you in a way that violates that contract, and we head into this wonderful world of undefined behavior where anything can happen, including formatting hard disks and just continuing to run as you expected without ever noticing. All sorts of ranges, behavior in between, but anything can happen. So you don't want to be in this domain if you can avoid it. But it's your responsibility as the caller, therefore, to satisfy those preconditions. And I said we might document certain precondition violations to say, these are a supported detection. I tried to open a file on the disk and I ran out of disk space. Well, you couldn't know about that. I'm going to spot that problem and say, I couldn't under the post condition, couldn't give you the file, but I'll at least report the error to you. That's something that you're not supposed to know in advance of calling me. Post conditions are my side of the promise. I say, okay, you've called me with all the right parameters, all the information that I expected, and I had to give you the behavior that you expected. So as long as you satisfy my documented preconditions, I'm going to give you the documented postconditions. So the issue is there's a little gray area between the postconditions and that says I'm going to tell you exactly what you get versus I'm going to give you a set of promises and there's a range of behaviors that might fall out. So, sorry. I'm taking myself down the detour when I don't have time on the slides. I'm just going to move on before I confuse myself further. Sorry. Yeah. Invariants is the another thing that you frequently want to document as part of your contract, specifically when you tend to be thinking about classes. Invariants are properties that hold of that class at any time a function is entered and exited. During execution of a function, invariants can be violated because you've got to make the transition from state A to state B somehow. But the guarantee of a class is that any time I have an object of that class, I can assume all the invariants hold. And if I'm passing one of these, a reference or a pointer to an object of this class through my code, on the convention of the people calling it, they don't have to assume this class is in some valid state or another. The invariant's guaranteed. This is what I can assume by that class without having to state anything more in the contract. Just you give me one of those, I know all the invariants hold. So that's an important way of consolidating and having some ease of how we can reason about things. We don't want to be spelling out your object in this valid state every time I call an API. The invariants say yes. You can assume the obvious does work. And error reporting says, okay, if I can fail, if you can call me in ways that I know I cannot honor those postconditions, I have two options. I can document some errors that will occur, and I can then hoist those up into the preconditions and say, as part of the promise, I expect you not to give me data that's going to fail the contract. So, sorry, I put the rehearsal on my slides. I'm having to read them at the same speed as you are, I'm afraid. I'm out of practice, which is terrible. The indication here is part of my nature of documenting my contract is I'm going to document the error code. So if I do return an error, you know how to respond. That's an important property of how you document and supply and support your contracts. So these are all essential properties of a good contract that you can read the documentation and know what it does and know how you respond to it. And the important point is that contract may document the errors reported for failure. And once you document a failure, those failure modes are now part of your contract. They no longer undefined behavior if you call in a way that is going to trigger those errors. Which brings us to another question. So far, I've been talking about contracts as a form of documentation, an essential form of documentation. And when you're trying to produce documentation, convention becomes an important part of that. And the question is, how much of what I'm suggesting is important, essential vocabulary for contract can we handle by convention? And certain things can be helpful, such as if I pass a reference, I can assume that there's a valid object at the end of that reference. The language enforces that. If I pass a pointer, I have to now document, do I handle things like null pointers? Is null pointer a valid pointer value? Or is that like any other invalid pointer value that doesn't point to a live object? And this is where your whole documentation base will start to acquire certain conventions that you will be able to assume globally across your contracts. Otherwise, your contracts grow very deep as you start calling out every single detail. So an important part of setting out your library specification, your contracts for the facilities that you are defining, is you want to establish a good set of conventions that go with that are intuitive and obvious, but hopefully also have a glossary somewhere that clearly defines where they're going to be. And let's not get lost down that one. But there's some common conventions we have in C++ parlance now that are associated with these kinds of rules that are, again, well known. People fall back on these. Has everyone heard of the basic strong and no-throw guarantees? Okay. So I'm slightly recasting those for the contracts in general. Is the basic guarantee is that if I call your function within contract, no contracts are violated, then whatever happens, whether it succeeds or fails, no invariants will be violated when I exit the function, and no resources are going to be leaked. The program remains in a good, stable state, whether I exit by returning an error code, throwing an exception, or completing the function in general. This basic guarantee is an essential guarantee for all software. If this doesn't hold, it's almost impossible to actually write functioning software, certainly to write reliable software. So that's why it's the basic guarantee. This is the essential assumption of I'm writing software, I've taken on board the notion of contracts. If I don't do this, I'm not even meeting the basic utility of my software on the idea of what a contract is. The next level up that's fairly useful to be able to reason about is what we call the atomic or transactional guarantee. This is a stronger contract, and it can be more expensive to implement. Sometimes it's free, which is why we like to offer it in those cases, otherwise it's an engineering cost to think about it. And the atomic or transactional guarantee says, I'm going to attempt this operation. It's either going to succeed or it's going to fail. If it succeeds, you get all the postconditions, everything's happy and great. If it fails, the atomic or transactional nature of it says, I'm going to roll back the request of the operation so it never happened at all, and the state of the program is largely unchanged. And certainly the state of the objects I was performing on have not changed. That's a particularly useful guarantee when I'm trying to reason about composing and building larger software, or particularly processes, to make sure that if I have a predictable system, if it matters to me at the end of that I have gone from state A to state B and now handled my error recovery appropriately. In order to implement the atomic guarantee, you often need to have some of your operations having what we call the no-fail guarantee. And these have really primitive contracts that simply succeed or fail. There is no try. So for example, here's something like integer arithmetic. It's always either going to succeed or you called it in some way that was out of contract, but there's no ability for this contract to fail when we're calling in contract. Which brings us to the notion of, once I've written all these promises and guarantees, how do I go about changing them? Well, if I've not released my software yet, it's relatively easy to change them. Because so far, nobody has tried relying on this contract. If my software is out, it gets a little bit harder. One thing I can do is, as I said, there's a huge gray area between, I said, you can call me with these preconditions, and I've not told you anything about my postconditions yet. Well, now I can start giving you a bit more detail about the behavior in certain circumstances. It might be we want a bit more detailed error handling in certain cases. So those kinds of things where we can narrow the postconditions give us one avenue that's relatively safe to change software. Often we can widen the preconditions and say, okay, when I wrote this software, I couldn't handle a variety of things, but this API has become fundamentally important and it's used more widely. It's become vocabulary in our system, therefore we want to handle a wider range of inputs that still satisfy the same range of outputs and the guarantees that people can assume there. It's very hard to widen the postconditions. So if I take a wider set of inputs and say, okay, I can now produce a broader set of outputs, any software that was already written against my original contract is not trying to handle this new set of outputs. So that's going to break someone. Likewise, if I narrow the set of inputs I can take to say I can't take as many inputs as subsets of arguments that were coming in as I used to take, clearly that's going to break some callers. So once you've published your contract, we have these firm promises people are relying on, it becomes quite tricky to evolve your software and move forward in an easy methodical manner, which is what I'm trying to get to with the second half of the talk. So, when it comes to changing a contract, your key thoughts at this point are risk management as much as software engineering. How am I going to safely roll out that change to that contract? How am I going to notify clients using that contract or calling that contract? How am I going to mitigate the kind of problems they're going to have? Often, as we say, the easiest solution here is I just provide a different API that shadows the original and has the new, more preferred contract, especially if, say, we're changing the nature of inputs and outputs, and then deprecate the original API and ask folks to transfer to the new one. This is about the most robust way to move things forward. But the problem is the old code somehow really never dies in practice, and we start producing a more complex system because now we're managing it old and new. This is where we come back to risk management, which is the better way to move forward when we have to make these kinds of changes. I say, the fundamental risk strategy is get it right first time, which is not great advice, But when it comes to trying to handle reliable software, and you're actually getting to the point you're publishing your library, it's about the best advice I can give. It's not the only advice. We're going to have the other half of the talks about that, but it really is fundamentally important that you release well understood and well tested contracts before you're standing behind those promises. So some terminology I'm just going to throw around that we've been using for the last probably about a decade or so on the standards committee now is the notion of a wide and a narrow contract. And this is fundamentally about the preconditions. A wide contract is a contract that simply whatever input you give it is valid. There is no undefined behavior or way to violate the contract with the arguments you call it with. A narrow contract is just what's different. If there's any undefined behavior in there at all, as soon as you've lost complete purity of, I have the ability to call this with anything I want, as soon as the client has to start themselves being responsible for checking the inputs they're giving to you, we call that a narrow contract. And the question becomes, which of those is better? So again, try a quick show of hands, see if folks go in these terms. Who prefers the notion of a wide contract?
From which perspective? From the client's perspective or the implementer's perspective?
From the client's perspective. You're jumping ahead of my slides. Okay. My general answer is yes, it depends. A wide contract guarantees there's no undefined behavior through your API. If your whole contract, the whole program is wide, you get something like Java, there's no undefined behavior, and it characterizes a set of erroneous or buggy behaviors you'll have to deal with that are a lot more predictable, and that's a good thing. Narrow contracts will often give you a simpler contract, which is easier to reason about, even if it puts a bit of the burden on the people calling the contract. And one of the benefits of the simpler contracts is simpler error handling. If I make all my contracts wide, I have to now diagnose and report a wide variety of errors. So when I'm calling that, I now have many more errors I need to be aware of. That I put the burden on the API developer to identify all those behaviors. Now I have to correctly handle them when I call it. So I move the complexity from I'm going to validate the input before calling you to I call you, you do the validation, and I now have to cope with whatever error handling you've given me. So the simplicity of having a wide contract is not always as simple as it first appears. So as Tim was saying, both have their place according to what you're trying to achieve. It's, hopefully the trade-off becomes relatively intuitive relatively quickly. So here's just a quick survey I did about trying to get the notion of how comfortable people were with wide and narrow contracts and types associated with those at the CPP con last year. I'm not going to take the survey here, partly because we don't have enough people and people aren't happy with their hands, but I don't want to take the time out to do it. But take a quick look and just get your general notion of, if you see in a contract these types, how comfortable or uncomfortable with you are you that you understand the kind of code that you're dealing with? So if you see an int, an unsigned int, or a double, do any of these raise red flags or concerns for you as either an implementer or a caller of that API? Just generally using these types. And these were the general results I got from CPPCon, that everyone loves int. There was not a whole lot of love for the unsigned int going around, and I was really concerned about how much love there was for double, because I was definitely in the 10% down here on the double. What I was trying to get to with thinking about this is, though, that getting people comfortable with the notions of how familiar their types in turn have very different narrow to wide behavior. The contracts on int are mostly narrow. And I guess in previous audiences, I've had folks saying they're very concerned about having narrow contracts placing too much burden on the user. But it turns out the type people are most comfortable with is int, where integer overflow is undefined behavior. There's, negating the integer minimum itself is undefined behavior. There's lots of undefined behavior associated with operations on integers. But people are generally very comfortable with them, mostly because most of those undefined behaviors occur outside the value range that they're typically dealing with, so they're mostly comfortable ignoring it, is my general perception. Unsigned int, on the other hand, is almost entirely a wide contract because all the overflow behavior here is well defined. Most of the operations on unsigned int are well defined. I got comfortable saying unsigned int is a fully defined operation, and then you go, oh, but there's divide by 0. So there's just a few little sharp corners, but mostly it's got a much more amenable interface in that we know what everything's going to do. There will be no surprises that catches out with strange runtime behavior when undefined behavior does anything it wants. On the other hand, it turns out people really like having negative values to say, I can see clearly this program has gone wrong, whereas I don't want to define a maximum number for my unsigned int to say I've now gone into bad behavior. So simply having that signal of negative to positive turned out to be a useful thing for many people, which is a large part of why the other slide, lots of folks were less comfortable, I believe, with the unsigned int, despite the more defined behavior. Double, on the other hand, has all sorts of wonderful corner cases and is almost impossible, I find, to use precisely, but it has a fully defined contract no matter which behavior you give it, because this is trying to work in hardware, and hardware doesn't want to go bang if you call it out of contract. It handles divide by 0. It handles doing crazy things like with infinities and negative infinities and raising 0 to the power 0. Who knew? This is well defined. And we even inventing not a number to say, well, now you have gone out of contract. Here's a state to just represent that. But the nature of double is it's now got a much more complicated contract to deal with all sorts of surprising corner cases, which are all well defined. But it's surprising that a lot of the information I get when I hear about people talking about double, you can't rely on double because it does crazy things. It's not well defined. Well, it's very precisely defined. It's just not defined the way you might like it to be. So just because something is very well defined doesn't mean it's as predictable and common usage as people expect. Again, just for clarification, typical surprising behavior is with double is that order of operations matters in ways it doesn't when you're dealing with integers, because of overflow and so forth. And again, in a similar vein, thinking about const char star, standard string view, and string as being on a similar spectrum, that const char star is a really weak contract that is compatible with C, but people like to move away from this towards string view. But string view isn't as wide as people like to think it is, because you still have to worry about dangling lifetimes when you refer string views to local objects. So it doesn't get the lifetime extension that returning a standard string might return. Standard string is good in all these circumstances, but it's distinctly more expensive than a string view. So after that high-speed attempt at an intro, let's have an example of what I mean in practice about when we're talking about a contract. So here's a simple function. It's sort. I'm hoping the name gives you an intuition of what it's going to do. So we're now going to talk about what we expect from this contract. First of all, what are the preconditions? And hit the room, right?
Reachability from begin to end.
So begin to end is forms a valid range, let's say, yes? Any other preconditions?
The predicate must define a big ordering.
Indeed. That's not quite how I phrased it, but I've got more than that. Any others?
The iterator should be directional.
The iterator should be bidirectional. Well, I might require that. I also know sort algorithms that work with forward iterators. I can do a merge sort, for example. But it does require the ability that I can iterate the sequence more than once. It's part of where this is coming from. The ones I had, begin and form a valid range. The range can be iterated at will. It's not a single pass iterator, because once I've gone past, I need to start moving elements around, perhaps revisit. The compare can be called to order any two elements in the range to know what that order is. Frank specified that more clearly in a way we had an additional constraint that I think I've missed. And the elements in the range can swap their values. So that's my essential set of preconditions on this contract. Have I missed anything? I don't think I have. That one's not a trick question, but okay. Is there a simpler way to write this contract? Well, if we're in C++ 20, we'll start using the ranges library. So rather than passing in a pair of iterators, I could pass in a range. And now my set of preconditions simplifies slightly. Now range is just a reference to a valid range. Most of the rest are fairly similar, but that is also guaranteed by the language and the preconditions on the range type itself. So I don't need to state those in my contract. Those are given by actually having that passed by reference in the interface. So the way I compose my interfaces out of different vocabulary types helps simplify the nature of the interfaces I have to write. Perhaps complicates life a little, that people need to know about these extra things, but here I'm passing one range instead of two iterators. So there's fewer things running around. It's hopefully less for folks to learn and understand their vocabulary. So when writing your APIs, think in terms of if you have useful common vocabulary that avoids you having to repeat things like iterative validity and ranges on every contract that I have using those types. Because, again, fundamentally contracts are documentation, and the easier your documentation is to read and consume, the easier time people are going to have using it, and the more they're going to want to use it. So, moving on to the postconditions. Unfortunately, I've got too many smart people in this room, so it's going to ruin the fun of this slide. But what are the postconditions on sort? Frank?
The range is sorted by the comparative predicate.
Indeed. What are the other postconditions?
The elements in the range are a permutation of the original elements of the range.
The perfect answer. This is the postcondition that a lot of people who do not attend ACCU conferences regularly miss. I learned this here from Kevin Henny, and it's been a staple of any talk, any given contract ever since, because that is too easily missed. And I've implemented many great, highly efficient sort algorithms that didn't have that second constraint. So I think that essentially is the heart of the contract. We've described the preconditions and the postconditions. Is there anything I'm missing? This is where we get into that nebulous gray area of, that's a perfectly good contract. I've still to spell out how I write it. But what else is actually pertinent that should be documented? Well, what haven't we mentioned? Complexity guarantees. Am I going to be happy with a bubble sort or a BOGO sort? Or do I need something that's going to guarantee no worse than n log n complexity? Do I have stability guarantees? That means I can't use quick sort and might need something more like a merge sort in order to preserve the stability. That's potentially extra cost.
Resource consumption, like stack usage.
Sorry?
Stack usage.
So do you want to document resource consumption on stack usage and so forth? Well, that's another good point. I've got something along that line here, not quite that one.
We did not say that the swap can't fail or that the comparison can't fail.
Indeed, we did not. So how are we going to respond to failures in those? Are we going to make them preconditions that they cannot do such? Is another important topic. Otherwise, we've got this hole in our contract. We don't know what happens when this does occur, but hey, we said we were going to take those inputs and we were going to sort the range somehow. So maybe that one's a buggy contract if we don't describe that information. So yes, what if any operation throws? We really ought to have an understanding, certainly in C++, of if I'm providing you objects that I control, because this was a template, so I control the types I'm instantiating you with, I need to at least have an understanding of how you're going to handle the things I give you throwing, or tell me I'm not allowed to do that. The one I had was, do we need to allocate memory versus how much stack space we're going to use? Quantifying that is hard. Saying that you might have to do it is useful. The one on the stack space is recursive implementations are going to use a heck of a lot more stack space than other implementations. That might be a concern. And the last one that I had was, are we going to potentially spawn threads and do additional work in parallel, which might have concerns for race conditions on things that might be reading that data if I've now got multiple threads all running around moving and swapping elements that my algorithm knows how to control, but if anything else thought that was. Or again, anything that might, as a consequence, block, if there's any blocking behavior in the operation, in the objects I'm working on in there, if they're smart objects. So these are additional things that either should be in our contract, or for things like the threading, the stability. Do we call threads in the C++ standard? We simply say that's not allowed across the whole library. So that's the kind of convention that you might hoist out to your library-wide conventions. And so the exception safety guarantees can be helpful here to say, well, I'll give you the basic exception safety guarantee. If I fail because you threw something, I've not broken any of your objects because that's my basic guarantee. I could give you the strong guarantee here, but I don't see how I'm going to do that without making a copy of your input sequence and sorting my own copy, which is probably a cost you don't want to pay. But I can make that interface and provide that contract. Second example. It's a really simple function. We're going to sum 3 integers. And my contract is return the mathematical sum of A, B, and C. Is this a narrow or a wide contract? Indeed, the presence of integer overflow means this has to be implicitly wide, so narrow. So the behavior is undefined unless the sum can be represented by an int. Is this narrow or wide? Why is it still narrow?
Because some of the value might be negative, so you might get a halfway through.
So as I'm going to do multiple arithmetic operations, any one of those might result in an overflow, yes. So that's from the was, does this implementation satisfy the contract? And yes, here's our example where clearly that is not going to satisfy the contract as written. So we've either got a bug in my implementation or in my contract. Where's the bug? The answer is, it's your choice. One of these is broken. This is clearly not a valid implementation of that contract. If I've released it into the wild, I'm probably going to want to try to honor that contract. But this is what I said. Coming back and documenting additional restrictions and narrowing your contracts gets hard. So let's try and say, this was a bug in the program, so we're going to implement it correctly. First of all, I'm going to see if I can trivially do this correctly. Otherwise, there's a few other options to say I can rearrange my operations accordingly because it's a mathematical sum. I can rearrange these operations to say as long as some ordering of them will fit and return, I will find it. I can implement that contract. It's just expensive. Maybe I don't want to do that. And then if we come layer through this, then you did call me with something that clearly I couldn't even represent the result. There's still a contract violation in there, but if you call me with parameters that I could reorder, I've done the reordering. So I can't read my own writing here. Yeah, I'm just annotating why that falls through that way. So, we ran out the contract with, we've discovered the important information is that if I want to use a simple operation, I can just say, okay, the sum of A plus B is representable, and we've already required that the whole thing is representable, and now this is out of contract. Changing the contract is probably the simpler approach here. Depending upon how risky I think it is, issuing an updated contract to folks who are relying on it.
Could you maybe use the undefined arithmetic?
Hold that thought.
You've just eliminated at least one possible implementation by adding that, having that extra clause. You have just eliminated at least one possible implementation of that function by adding that extra clause to the contract.
I don't see how that has eliminated any implement. That might not honor this contract, but it doesn't change the fact that either of those you're saying I've narrowed this to say that other implementation. Yes, correct. I have chosen a form of specification here that has picked that ordering and said, okay, is that I might not have constrained the implementation that I've got to use to honor that contract, but have I constrained it to accept different data? From a caller, is the difference in implementation perceptible? And I believe not. So I might argue with the, if you cannot detect the difference, your other implementation would be valid.
I think, I'm going to have to think about that for a while. I think that you have, in fact, eliminated, you have made it so that there are some inputs that are now out of contract for one implementation and provide undefined behavior on the other. But I'll think about it.
Yes.
I'll let you.
Given I'm making this all up on the fly, it wouldn't surprise me that you're correct as well, because you're a smart man, and you've done this before as well. So we come back to the question of, is a narrow or a wide contract here better? Clearly, we don't like the expense of that whole huge, narrow contract implementation of where we honor the contract. But again, if folks were relying on that contract, we had a bug. Maybe we can narrow this contract, because the bug meant they weren't getting the behavior they wanted anyway. So perhaps this is a place where we can move the contract forward. But rather than going to unsigned, I went to long, which on most implementations would also let me resolve this, with the proviso that size of long is larger than the size of int, which I can statically determine. And again, that's probably the simplest implementation that gives us closest to both. But the expense is we're now doing our arithmetic in longs rather than ints, which is possibly the expense worth paying. So that's my basic introduction to contracts. From here, I want to go into the library facility we're now providing to make it easier to work with this kind of contract. So quick plug up front, BDE, it's an open source library published by Bloomberg that basically adheres to the John Lakos School of Software and Philosophy of Design. And this contract checking facility is right at the base foundation layer of this. It doesn't provide as a separate facility, but even if this is all you want to use, it's possibly worth checking out the library just to get this, because I find it indispensable even for my own code. Writing hobby projects at home. So what are contract checks? I said we're going to have a contract checking facility in this library. Contract check is an attempt to identify the misuse of a contract. We're going to try and find your errors. And there's several ways we can do that. If we're trying to find errors in preconditions, that's errors of people calling our code. So the only way we can do that is we're going to have to write checks in our code to validate the inputs to say, you called me out of contract. On the other hand, if we're trying to validate postconditions, I don't necessarily want to pay costs for that at runtime. Those are much more easily tested by test drivers. So the question is, why do Bloomberg folks keep talking about test drivers and not unit tests? To an extent, a test driver is a very specific piece of software the way we write our code. All our code comes out in what we call a component, which is a header CPP pair. The test driver tests every contract in that associated piece of software. So it's a single file, it's a single test driver, as opposed to spreading checks around a variety of places. So unit testing is kind of in that space, but we do mean a little bit more specific that we've got one test driver that's constructed with a semi-mathematical, we don't rely on any behavior that we've not already tested and proven to be correct. So it kind of builds up as a proof that this functionality all works, as opposed to pulling apart each individual part and testing it in isolation. Of course, there's always a bit of bootstrap, because how do you test the first thing until you... But modular a little bit, very, very base level stuff. We try and build a testing philosophy around, the test driver. Unit testing could be another term. It's distinct from integration testing, definitely. So, detour into terminology. So, but yes, test drivers are how we validate all our postconditions, and we will exhaustively test every possible range of valid inputs or representative range. We'll determine, how do we determine what a good set of inputs are to test the breadth of behavior of the contract? There's an awful lot of that coming up in Dylan's, not his current book that's coming out, it's Christmas, but his next one or the one after that. But testing is a very big and well thought out part of the philosophy here. And invariants are something we don't talk about as much, I'm afraid, and they tend to be tested in destructors because testing them at all times and all places can be expensive, but you want to know if your invariants have been violated. The one place every object is almost guaranteed to go through is its destructor, so that's a good place to provide a final check to say, has something blown up when I wasn't paying attention? So, if we take a look at what the C++ standard offers, it offers exactly the same thing as the C standard. It offers the assert macro, which is the most primitive check we can have here. It's going to check the expression you supply it, and if that expression, that predicate, says this thing must be true, turns out to be false, bang, we're going to abort and terminate, well, abort and kill your program. Terminate's a different thing. Similar, but different, it's C++. And if you define the ndebug macro, all your tests vanish, they no longer execute, which is unfortunate if you had side effects depending in there. And but it's efficient because you're no longer paying to actually do that validation. So the general notion is, do all your testing with assert macros on, see if anything crashes, then yay, we can go and deal with the little error message that came out from that. And otherwise, we're going to release our software without these checks enabled because people don't like software crashing at runtime with these messages. Typical workflow. Not a whole lot of customizability here, but so we've got a relatively low bar to try to beat with our library. So, key issues. The release build just eliminates code, so it's no longer being checked unless you're running without the ndebug macro. So, if name lookup fails or you've got some funky syntax errors in there, they might not be detected for quite a while until somebody builds in the other build mode. Side effects, because of the nature of macros, are going to go missing when you start testing with them without those ndebugs, and that can be surprising. As an invalid code no longer seen, compiler warnings in subsequent code may rely on that omitted code. And the abort behavior is not appropriate in all cases. Now, I'm afraid because the facility we're going to talk about is a macro facility, we're still going to have issues with side effects. So generally, just don't do that. But hopefully we can have an approach that will at least expose some of these issues more easily. So what features would we like? Sometimes we have expensive checks that we would like to enable in particular intensive audit checks when we're trying to, our brains are melting saying there's a bug here, I can't find it. And checks that I wouldn't normally be prepared to pay for even in a regular debug build. I want to have some ability to still check for, okay, I'm doing a binary search and I need to confirm that the range that you gave me was sorted. That's way more expensive than the operation I'm actually trying to perform. But when I'm trying to start finding these errors, sometimes having the ability to run those checks is very helpful. So some way to distinguish expensive checks from typical cheap checks. The ability to control how we respond to the errors or the detected violations. Abort, as I say, is not always the right response. And we're going to talk about a couple of ideas of how we can use different responses as part of our workflow. And ideally, we should not ignore ill-formed code. So in the case where the macro says, I'm not evaluating that, ideally, you should still parse the code, and so your code stays well-formed for when you do turn them on. So the BDE contract facility is basically a set of customizable macros that allow us to install a violation handler to control that behavior. The macros can describe the cost to say this is a cheap or expensive thing that I can separately control when I enable them, and we have a dedicated workflow that goes with those. So, introducing the workflow. What's the first step? Now I'm going to try and introduce contracts into my code.
Include the right header files.
Sorry?
Include the right header files.
Include the right header files. I'll go you one better, even more primitive than that. I don't have the header files on these slides, by the way. Let's just write our contract. If we haven't documented it, then it doesn't exist. So first thing we're going to do is write our contract, and I'll now find out how small this font is on the screen. So I'll read that out just so we can see the contract that I'm documenting. The function is find, takes So it will return the address of the first int in the specified range that's given by begin and end that has a specified value, which is the argument I supply, and return the last, oh, I changed my name so I was writing this contract, return end, bad slide, if no integer in the range has that value. And the behavior is undefined unless the range begin to end is sorted. Does this contract make sense? It's not quite binary search from the standard. It's I'm going to find you the thing that was there or tell you it wasn't there at all. So, any additional things you would like to see in this contract that I haven't mentioned? Well, this is the contract we're going to work with for the rest of the slides. For a start, I forgot to mention complexity up there. But complexity is hard to test for, so for the purpose of enabling my workflow, it's not as relevant. So that's the contract we're going to work with. Here's a primitive implementation that I believe actually does the job. So I'm not going to spend too much time dwelling on that. But we get down to the workflow, which is the basic topic of this talk, was the title. And the workflow is going to go through 4 stages. I want to ignore my contract, inform myself about errors, enforce detection, and then finally assume and enable the optimizer. So ignore, I'm going to insert checks into the code that are deliberately going to be ignored. They're going to be predicates that are never evaluated. They're not going to run at runtime at all, but hopefully now they are going to be parsed. Then, once I'm happy that I've got all my checks throughout my code that I want in the places I need it, I can switch to inform, where the program will now evaluate those checks, and I can now inform myself that if those contracts are violated, I can write a little bug report, something out to log file something, but continue running. So I make no change to interfere with buggy programs. They continue to run and behave the way they always have, but I at least now get error reports where I need to fix. At some point, hopefully my program's now running clean, I can switch to the enforce mode to say, okay, now I know my program doesn't have any of these issues. I can make sure they don't creep back by switching on the enforce flag and saying if anybody does violate my contracts, they will now get these hard errors when they're running the program. And once that has been released in production for a while, I might decide, you know, rather than running those checks, I really want my program to run faster. If I assume those things are always true, perhaps the optimizer can make certain additional optimizations on my behalf. But first of all, I want to make sure my program is correct before I enable the optimizer to act on that. And the key stage is, this is how I can now introduce contracts or change contracts in an existing piece of software. Because the key first step is we're going to introduce our contract checks without actually running them. This is simple. We just pass the program, and the macro now has to expand into something that still has the code in a valid place, but it's not going to be called. So have it in a lambda expression that I don't evaluate it in a size of operator because I know it's got to return a Boolean predicate. I can have a true equals or something in the size of, and play around and find the form that doesn't actually give warnings on unused values. Because compilers like to do that. And this guarantees that if I start introducing errors in my contract checks, the compiler is going to tell me about those up front. So that's a relatively simple first step. What does that look like? BSOS review is the name of our simple contract check that will do this. So in my contract here, I want to make sure that begin end is a valid range. So either begin equals end, so I can support null pointer ranges as empty. Don't see why they should be called out separately. Or begin is less than end. If begin and end are not in the same range, that's not something I can easily check anyway, because that's undefined behavior at the language level, and I'm not going to try and determine if these 2 pointers are comparable in the first place. I could go through standard less in the standard library if I really wanted to force that into a well-defined behavior, but I was trying to have something that would fit reasonably on a slide.
Would you want to add a test for begin and end not null?
Yes, I just realizing in hindsight that I hadn't put that test in, because I thought, I thought I was doing that on the or with a big equals end, but yes, I switched to the,
No, I mean,
yes.
when one of them is not.
Do you think that's helpful to like have two operations check there? Later an error occurs and we don't know which one is any?
Excellent point. So, is it a good idea, like as I have done here, to conflate two checks into one assert macro? And generally the answer is no, for the reason given that if I've got a failure, I want to know which thing failed. If I've got a variety of checks, I'm going to be left with too much information to try to figure out runtime. Well, I don't know which one of these is failing yet. The intent was I was trying to do what Marshall said and then got too clever just as I was going to publish a slide and thought, oh no, I've got a better check to do here. That was supposed to be the same, or what neither is null, which would all have to be one check. But I was trying to get a check that depended on if I'd got two null pointers, I wanted to exempt that with a short circuit before I got into the second part of the check. I wrote a bad check for what I was trying to demonstrate though. You with me, or I just gone off on a wild detour? Let's clarify here. The issue I was trying to get there and displayed badly is, because you've got short circuit Boolean operation in C++, if the second check was valid only if the first check succeeded, that's what I was trying to get into the predicate, to say sometimes these slightly more complicated preconditions are useful, but generally, yes, you would rather have separate precondition checks just so you know which one has failed. I saw a hand going up.
Could this be aligned or test the alignment?
So I'm having a hard time hearing.
You could maybe test the alignment of the two iterators to make sure they match.
So question is, I could test the alignment of the pointers to make sure that they were valid in that sense. I could. Is that?
I think that might be a requirement, language requirement.
But as I say, I believe the language already requires that those pointers will be well aligned, or else I violated the language in getting here. So.
In case of alignment, it depends completely on your hardware, how it is configured, whether it is a requirement or not. And we haven't seen that requirement in the contract of the function, so checking it would be a little bit underhanded.
So Till's observation is that how alignment interacts with the hardware is often platform dependent, and whether or not there's a strict hardware requirement on alignment here is going to vary. We haven't written about it explicitly in the contract, which is a good point, but if we thought it was an important thing that we should be concerned about, we should add it to the contract and check it accordingly. The point of this slide, though, is to introduce the BSOS review macro, which is in the BSOS review header. I went out of space on the slide for the hash includes because you can see I'm already filling too much space. To say this is how we would now introduce this check into the code. I saw another hand going up, and I'm going to move to the next slide.
There's even more to check whether something is valid range, because both could be valid pointers. The memory space in between might not be accessible for example.
So I'm getting some very good questions about things that mean this test is not sufficient to validate the contract. And I think actually, I don't have a slide on this. I should have put a slide on this. I'll jump out and call out at this point. That is completely correct. When we're providing a contract checking facility, we are not trying to be exhaustive and catch every possible abuse of every way I can call this function, because often these things are not determinable. I pass you a pointer. Is that pointer valid? Is there a live object at the far end? Maybe there is when you call me and somebody destroys it. I don't know. I don't have the ability to write a predicate to determine that. Perhaps I can write something up that other tools can interact with. This was one of the features we were looking at when they tried introducing C++ contracts into the C++ language, that we might provide annotations for things other than the compiler to reason about. But in general, there's a whole variety of things that I can't check, and I'm not going to try to, because it's not my job ultimately to find you and your bugs and tell you everything you did wrong. But if I can find the easy stuff, and help you find those bugs, this lets me do that. So it's a tool to help me find easy misuse. As I say, there's expensive operations I'm not doing here. We'll come back to those later. So I'm not trying to capture every possible misuse, but I'm trying to find what are the easy and obvious ones that I can easily encode and would be reasonably cheap to run when I wanted to enable them. Does that make sense? So this is the basic idea. We introduce the test with BSOS review. The next step, we now want to start evaluating those checks and reporting errors that come out from people calling us out of contract. They've got bugs they need to fix, even if the program seems to be doing what they wanted it to be doing. So again, we are not changing the existing program behavior, other than the fact we are now running the predicates on logging. So perhaps the nature of the runtime performance might observe somewhere, the file system access from writing out to log files or wherever else I'm doing the logging. Sorry. Logging might show up, but essentially the logic of the program is not affected by this. So we switch a build mode on the command line. In actual fact, this is our default. If you want to go back to the previous one where you just check the predicates, but don't evaluate, that's the one in our configuration you pass the flag to, like ndebug. Because my typical behavior is, in existing programs, as I'm writing new APIs, I can go straight into the review. If I'm introducing into existing live software, I might want to go through the other process. But by the time I've compiled the code, mostly the inform is what happens when I turn off my checks, as opposed to something, it's my safety net, rather than I'm actually going to write the software. I will start at the inform level. So what we're going to do, one of the features of the BD facility is we can install custom violation handlers to say, when I spot a violation of a contract has occurred, I'm going to go off and call the piece of code you've given me to say, what do you want me to do? And that's where I can write my logging functionality. Write to a log file, open a bug in one of our bug databases. We have a default violation handler that goes with the review that does an exponential back off, so that if it turns out you're calling something in a tight loop and it's all the time violating the contract, you really don't want to have 4 billion entries in your log file by the end of the day or the end of the hour. So exponential back off there turns out to be a useful facility, but the point is you want to be able to run and start getting logs from folks who are using your API, especially, as I say, the notion is I'm now introducing a check into, I noticed that my sum of ABC had a narrow contract, and I've narrowed my contract, I want to publish that. So I'll now publish it with a review check in place that will find out if anyone actually is calling it out of contract. They're going to have to go and fix their code before I can do anything more permanent here. So I can now put this out and run this for a while. It looks exactly the same, because the only difference between ignore and inform is the switches I'm passing on the command line. But now I can run this, get feedback from production, see the reports coming in, chase down my colleagues until finally our system's running clean. None of these errors are showing up in running systems. We move to the next step. We can now enforce the contract. And what we're going to do here, this is more like the traditional C assert. When we spot the violation, bang, we're going to kill the program straight away with a call to abort. So this is going to change the behavior of your program if a contract violation is detected. So this is why you're a bit more cautious before you jump up to this final step, and that's why we want the inform to get here. The principle is the checks are going to be enforced, and you cannot resume the regular flow through the program that the inform did. Which means that inform could still be very buggy, running into programs that would then have their own undefined behavior and failing in spectacular ways. And you weren't protected against that. Now you're protected against the consequences of a lot of these bugs, because we're going to tear the whole program down and abort. But the violation handler is customizable. So one of the things you can do with this, you might choose to say, well, I'm going to install my own violation handler for the enforce mode that says, rather than abort, I'm going to throw an exception. Many folks are uncomfortable with the idea of exceptions as an approach to precondition violations. But in a very specific case, we find it extremely useful if we want to test the coverage of our assert macros. We can actually run this facility in a test build mode to say, I want to throw exceptions of this kind if I trigger a violation. Now we'll then call it specifically out of contract in many ways, just to see and make sure that the correct handlers are coming up and I've got the test coverage I thought I had. So the ability to throw, as opposed to just always abort, at least makes the facility testable and retains a guarantee that you're staying away from the protected behavior that you didn't want to release the hard undefined behavior that might be a consequence of violating the contract. So you gave me a null pointer. Well, okay, I'm definitely not going to go off and dereference that null pointer in the code that follows. By default, I'm going to abort, but you have the ability to put your own custom handlers in.
So I have a question. If you are enforced macro throw, that means you can't mark any of the functions as not set. How do you deal with that? Because like function that just adds two numbers will be not set, right? So like how do you get out of
So-
this contradiction?
So the question is, how do I handle no except in the system? Well, first of all, the enforced macro we're about to see doesn't throw. It calls the violation handler. But the user is allowed to install a violation handler that throws. So yeah, by the back door, it can throw. And the question is, how does that interact with no except? And the answer is badly. Which is why you'll see in the C++ standard there's been a convention that we do not put no except on narrow contracts, because that is the language getting in the way of the library's ability to try to help callers when they call the function out of contract. Perfectly reasonable for the library to do anything, unfortunately, or to trigger undefined behavior its own way, because you had no guarantees. But if they're trying to do something and help you, if you put no except on your function, you're putting a barrier in the language to how you can respond to those contract violations. You might still choose to do so. You might have good reasons that you want to put no except there. All these things are an engineering trade-off. At Bloomberg at the moment, we're not wowed about adding no except everywhere, so it's not been a concern for us. I know within the standards community, a lot more folks are much more keen on having no except everywhere. And again, in the standard contract itself, no except is left as a quality of implementation issue mostly.
Wouldn't the trap be a far better solution, more easier to get a full stack and more helpful?
So the question is, wouldn't a trap be a better answer? And yes, I mean, the trap with the abort and the call stack and all these things are a much better solution in a deployed production system.
Even if you're in development.
Yeah. They don't support testing for the facility as well. And in production systems, there are other strategies some folks like to deploy, such as when I'm trying to say, okay, I'm going to have to tear the system down, something bad's happened. I want to somehow save your data. I don't want to overwrite your original files because that would be a really bad idea. But I want to put save state somewhere so you can try and recover the in-flight work and see what was going on. And the ability to handle that sometimes doesn't work so well with no except if that might be handled through, passing through a few layers of stack unwinding with exceptions. So there are other reasons other than just test drivers. But again, different software companies, different software houses have different strategies of how they handle some of these things. And no except is a contentious issue in some of these places because it inhibits certain error recovery or bug reporting strategies. So, anybody want anything more on no except before I move on? So, the way we switch to our enforced mode is we take that BSOS review, we turn it into a BSOS assert, which means we need to include a different header because that's in the BSOS assert, not the BSOS review header. But believe it or not, we thought about this. It's deliberate with the same number of characters as review, so you can simply search and replace it, and it's not going to mess up all your code formatting tools. Everything will just align just the same as it did before. So yes, when this goes, it's now, we're at least guaranteed we're not going to go into the following code. We're going to have our violation handler call into whatever we did. And if I install a violation handler that simply returns, which I'm not supposed to do here, the assert macro itself will then abort. So even if I install a violation handler that tries to return to the caller, this macro is going to guarantee that doesn't happen. because that's the essential property we're trying to enforce here. So the whole notion now is, I run with this, my prediction systems are running happily. Yes, I do still have a screen.
The screen occasionally will.
Yeah. I'm happy that this is all working as intended, and I really want to eke out that last bit of performance from my system. Well, that's when we can switch to assume. And we want to say all those tests that I was asserting on before, now those, I don't need to test them anymore. I'm going to take them as a hint that they are always true and pass some hint to the compiler that the optimizer can reason about these predicates being true. And that can lead to certain code allusions where it can backpropagate. Well, I know this pointer is not null, therefore it looks like you called me with what might have been a null pointer here. That branch couldn't happen either, and I can eliminate more code. And there's a wide variety of things compilers get really smart about reasoning about impossible things so they can just elide whole chunks of code that actually can't happen as long as all the contracts are followed. So the way we do that is, well, just think I've not put anything else here. So the way we do this is we can now introduce in our macro, when I expand into the non-evaluating form, I can say make sure that this contains some undefined behavior that's easily exposable to the compiler, so it can then reason about, okay, I'll force that undefined behavior early rather than where it might have happened in your function, deeper down, and that can then propagate back through the system if it's an inline function and so forth appropriately. Again, ideally, some compilers even come with things like an assume inbuilt intrinsic that makes this kind of propagation much simpler and easier to reason about at the compiler. But even without that, you can usually trigger some kind of clearly undefined behavior that compilers will reason about. So again, same workflow. All we're doing at this point is we're now passing the command line option to the compiler to say, whenever I see an assert macro, expand it this other way. Which leaves us with the other question I had, which was, how do I handle expensive checks? And first of all, how do I measure an expensive check? What does expensive mean? In different notions I've seen of expressing complexity here, we might have a scale 1 to 10. 10 is expensive, 1 is cheap, and I can set my threshold somewhere in the middle. There's simply how, as things get more and more expensive, I'll just keep putting up a number without bound and arbitrarily pick an expensive. I want to have costs, run checks at this cost or less. Or we could have something just as simple as says, you know, a check is either reasonable, expensive, or cheap, high, low, either side, and assume most of somewhere in the middle. And from a practical sense, we found that this high, default, and low cost was the most useful model. As soon as you try and get anything more fine-grained, people have to think too hard about deciding exactly how expensive their thing is. And then it becomes such a complicated, awkward feature, they just don't use it at all. High, medium, and low, high, default, and low is a reasonable model. People can understand this is what I'm expecting, and if something wildly is outside that range, they know that's expensive. The low, cheap cost we've not had as much useful experience with, and we're looking to elide that as we go on. I don't actually have any more slides on that. They dropped out at the last second. So how do we rate a cost? Well, there's two main things that will make a check expensive. It's either going to have a really large constant factor compared to the rest of the function that you're evaluating, or in the worst case, you're going to change the algorithmic complexity of the function, such as in the case we're looking at, where determining that I have a valid range, that everything is sorted, is going to violate the complexity assumption that I'm going to do a binary lookup. And going the other way, sometimes you have the tests that are absolutely critical that if I spot this error, the consequences, if I let the program continue, are so catastrophic, I absolutely have to be sure I bring this program down, come what may. Now, we used to have a macro mode that covered that, I believe. It's still in our library. But the recommended best practice here now is, if it's so critical that I have to bring the program down if I spot that error, it doesn't belong in a macro-based contract checking facility that could be turned off in some mode. That should just be actual program logic. So we no longer try to address that within this facility the same way. So how do we indicate expensive checks? Because we said it's just there's a default check and there's an expensive check, we have a variation of the macros that just append _safe. So that, here we go, if I'm trying to now, I've got my whole code in production here, and I want to, I'm still seeing some problems now, I want to run them through my test drivers in a mode that wouldn't be good in the production system. I can now review safe is sorted on that range. Expensive check. Hopefully I'm going to either run clean and go, okay, I was thinking about the wrong thing, that wasn't the problem here. Oh, great, somebody's now calling me out of range. I can hopefully get the stack trace and say, okay, you've called me with an unsorted range, and dispatch a bug ticket in the appropriate direction. Similarly, there's a assert safe. If I'm really happy with the review safe and want to move into the version that will absolutely kill my software, because the assert was written before the review, that made a lot of sense to me back in the day. In practice, I would expect the asserts to be caught at the review stage and would not want to be running production systems with safe, expensive checks in them. On the other hand, I might want to have the optimizations coming out of these when I switch on to the opt mode, or the optimal mode. So, reviewing the workflow summary. First of all, we're going to introduce introduce our checks into the system. Again, we're not trying to catch every possible misuse of the contract, but we're saying, how can we introduce contract checks and allow us to potentially evolve our contracts by introducing checks if a contract has to narrow and tighten up from the contract it used to have. Go through the inform stage, where even in production, we're now opening up these bug tickets and getting the reports, as long as we have some way of collecting the telemetry of the reported issues. Then we can switch on to the more traditional and force kill the program if these bugs show up, with a nice, happy assert message popping up to the user saying, hey, user, here's some crazy code that means something to the people who wrote the software, but means nothing to you. And ultimately, we then get to, I think it's much more in Timur's concern, get to turn on the assume mode, where the optimizer can now start taking advantage of these same checks. The nature of the library is, on the command line, we configure and disable the whether we're running the checks and continuing or not. The key difference between review and assert is that review will continue into your function body and continue running, even if that has undefined behavior, you've not protected yourself against the bugs. Assert will guarantee you're not going to hit those undefined behaviors in that might result in your function, because we're guaranteeing we're coming back out of this function. Ideally, we're going to terminate the process at that point as well. So the key issue, you've got the review and assert is the one dimension, and the command line then switches between, are those going to be an ignore on the review or an assume on the assert? Because whether or not you evaluate those contracts says which of those behaviors you get. And if you want to enable those more expensive checks, that's where the _safe macros come. I ran through it about 10 minutes faster than I thought because I gabbled my way through the opening material. But yes, please check out the BDE libraries, and in particular check out the BSOS assert facility at GitHub at the address given. And I've got 10 minutes for questions.